Thanks to the organizers for the invitation. Thanks everyone for being here. As the title suggests, today I'll be looking at the Lotka-Volterra system and explain how one can use model theory to study this differential system. But let me just point to what is the general problem we're looking at. So this is a general problem in differential algebra, where if you're given an ODE or a system of differential equation. So in this talk, we will mainly be concerned with nonlinear ODE. So what you want to do is to classify all the algebraic relations between solutions and derivative of that system. So now this is stated a very sort of general problem, but it turns out that we don't have necessarily many tools to tackle it the way I said. And indeed, what I'll just do in a moment is write down the full list of equations for which we've been able to do that. And unless I missed something, and please let me know, this is the full list. So the first equation, the first bunch of equations, so let me just say this off. Equations, we have a full answer. So the first result I know of is Brestovsky in 1989. Where he looked at second order equations of the form, so where here R is a rational function. But for very specific rational functions, so I won't spend too much time saying what they are, because somehow more recently in joint work with James Freitag, Remy Jaoui, and Dave Marker, so this is 2021. We are able to tackle any rational function and decide precisely when to classify all algebraic relations. And what we show is that for the condition on the rational function that guarantees that there are either no algebraic relations at all, or if there are finitely many of them. But this is sort of what we have. Another, more recently, is the work of Pilla on the Ax-Lindemann-Weierstrass 4J. So let me just say that. So Pilla, and I'll say indirectly. So here, so the Ax-Lindemann-Weierstrass 4J. And so what's done here is, well, we've seen in the talk of Sebastian that we have these modular polynomials that vanish on JT and J, let's say GT for G in GL2Q plus. Sebastian didn't directly say it, but he pointed to the fact that these two satisfies the same differential equation that he had written down there. And so these gives algebraic relations between those solutions of that equation we saw. And it turns out that these are the only ones. And the Ax-Lindemann implies that. So that's, and then in joint work with Casal, Freitag, myself, we do the same, but for Fuchsian automorphic function. Oh, so I should say this is not accurate. What I mean here, the full answer, and I should say for this talk, I'm going to only consider an autonomous ODE or system, and I'm going to consider the order of these things to be bigger than 1. Okay, so the case order is 1. There's work that is slightly different. Indeed, there are sort of very recent work that's related that allows you to say a lot more. But for nonlinear, as I said, so and it turns out that this is everything. So now, while that is, well, one could say, well, maybe these are interesting equations. This is what we call an equation of Leonard type. So appear in some physical contexts. And these automorphic function, obviously, the differential equations are the unifying function. So one might say it's because it's very interesting, this equation. But another reason, of course, is that we don't have general methods to tackle those. And except for the Pilar result, which uses ominimality, all the others use the Mole theory differential fields. Okay, and so today what I'm going to present is yet another example of an interesting differential equation that we are able to sort of give a full classification. And I'll explain the techniques that we use, and many of them are part of the proof for these equations itself. So let me go ahead and state our theorem. So I'm going to consider the Lotka-Volterra system. So, which is given, so I'm going to call it LVABCD, which is the system given by so where A, B, C, D are non-zero complex numbers. So this is the Lotka-Volterra system. Generally, when one works with a system, one is more careful about the parameters. They're chosen to be real numbers. Usually one assumes this model, the predator-prey competition model, so one assumes something about the arity of whether it's positive or negative, but somehow we works in a more general setting. For us, the Lotka-Volterra system is this very general system, so it includes the one that people work with. And our theorem is the following. So this is joint with Yutong Duan. So my PhD student, unfortunately, couldn't attend the conference. So assume B and D are linearly independent over Q. Take x1, x y1, xn, yn, distinct solutions. You can think of them as meromorphic on some little domain, that's fine. Or in differential algebra, we simply will take it in any differential field extension. Then what we have is that all the solutions are algebraically independent. Oh, sorry. So assume further that, so here, I want to assume that the solutions are non-constant. Sorry about that. And non-degenerate. I'll say second what it is. Then the solutions are algebraically independent over C. Okay, so I'll say the transcendence degree over C of C with all solutions is exactly 2n. right? So, and what this is saying is we've achieved there are actually no algebraic relations at all, okay? So what do I mean here by non-degenerate? So I mean neither x nor y is equal to 0, okay? So that's what we want, okay? And so what I'll do is I'll try to explain what are the model theoretic tools that one needs to prove the result, and then comment on some of the open problems we have and also progress that's been made. So now, if you've seen me talk about these functional transcendence results before, you know that one thing, one strategy that we've employed numerous times, starting with work with Alan on the Pennever equation, is begin by showing that these equations are what we call strongly minimal or irreducible. So let me start by going back to the definition of those and then sort of explaining how one can prove that. So that was the introduction, but my real start now. So strongly minimal autonomous planar system. So, all right, so many things that I'll say here is more general than that, but given that we're working with a planar system, it'll be enough if I simply restrict to that setup. So we'll do that. But first, let me just fix some of my notation. Throughout UD will be a universal differential field. And I'm going to assume that it's differentially closed. So any finite system of differential polynomial with coefficients in U, if it has a solution in some extension, already has a solution in U. Universal here is in the sense of Colchin, so universal domain for me to work in. So when I talk solution, I'm always picking solution in U. When I'm talking about field extension, I'm always talking field extension within U, all right? So I'm going to assume that, the constant, the kernel of D, let me use Sebastian notation, is the field of complex number. So I can assume that by making an assumption on the cardinality and U, for example. All right. All right, so now I want to work with autonomous planar system. So I would have fixed a fixed subfield, let curly C be finitely generated over Q subfield. And I'm going to assume that it's algebraically closed. All right. So here, for the setup of the LV system, curly C will be Q adjoint those parameters, right? Say it again. And I assume it's algebraically closed. Finite transcendent theory. Thank you. Finite transcendent theory. Thank you. All right. Good. All right. So what do I mean by a planar system? So let Fg be in curly C of xy, a a planar system, for me, in this talk, is one of the form so I'm going to call it S. X prime is F X Y. Y prime is G X Y. And my aim now is to sort of define what I mean by strongly minimality. Okay. To do this, let's look at the condition that I want to assume that we have non-degenerate solution. So non-degenerate solution. So of the Lotka-Volterra system corresponds to subsystem. So one is of the form x equals 0, and it's not hard to see if x equals 0 that you have the system y prime is dy. Okay, and y equals 0 correspond to a system y equals 0 and x prime is bx. All right, and so somehow these non-degenerate systems actually correspond to the fact that the Lotka-Volterra system I start with has this subsystem sitting there, right? And strong minimality will be a very strong way to say that there are no such subsystems. All right, so let me try to make this clear. So given the system S as above, we can define any differential field extension of C. So a differential field, let's call it K. What we have, we can define a derivation. So ds on kxy, indeed on rational function. So as follows. So ds is given by d plus f. The usual thing, so if you've seen that before, fine. And so how do you differentiate an element? So if P is in K xy, so remember this is an extension of our base field C. So ds of P is simply going to be, well, so I'm going to write it as that PD plus, right, applying the rest of it. So all I have to tell you is what PD is, where, so PD here is a polynomial obtained by differentiating the coefficients of P, right? Okay, so if you define this derivation, so if you define this operator, you have a well-defined differential derivation on the polynomial ring, indeed on the ring of rational function, field of rational function. And so this, using this derivation, I can now define what I mean by a subsystem in a more general term, in more general terms. So definition. So a polynomial in kxy is ds invariant. Or I will simply say invariant if the S is the system is clear. If there is a polynomial Q in KXY, so that when I apply the derivation to P, I have that product of polynomials. Okay. Yeah. Right. Yeah. So you apply the partial derivative to the polynomial, and then you multiply. So it's simply what you would do normally.
Yeah. So you don't have anywhere you apply the same you apply to the coefficients.
Yep.
Right? And then you apply to the x using the root from that. You apply it to x.
No, you apply it to x like d by, so it's a polynomial, so you apply it to x. You simply differentiate with respect to x, treating y and every coefficient in P constant. Right. Yes, exactly. Yeah. Thank you. So what are sort of subsystems, what we consider subsystems? So if a P is a DS invariant polynomial, and I is the ideal generated by F, is such that P. So I shouldn't change your notation in the middle of a talk. Such that, so it's not a zero ideal, and it's properly contained in KXY. Then we call the zero locus VI an invariant curve. All right, so and let's see these examples. Let's see how we get them from the invariant curve. So here's example. You can see that P given as xy is an invariant. Polynomial for so LV ABC. Indeed, it's not hard to check that I should say that, so it's not hard to, if you compute this derivation, that you can rewrite this whole thing in terms of the original P plus this as Q. All right. Okay. Oh, yes. And I should say, usually we say that this is a DS invariant curve over K. All right. So somehow, because the system is defined over C, the field of constant, and you've gone to a differential field extension to find this DS invariance curve. In this case, you didn't have to. The invariant polynomial was already over the same parameter you started with. All right? And so now I can put in the definition. So definition So this is the definition of strong minimality in this very particular setup of planar system. So let curl S be a set defined by xy in so I don't know. So xy solves. Save me some time saying that. So two solutions in my. You remember I work in my field U. So I'm looking at U that solve a fixed planar system that's given. All right. We say S is strongly minimal. If for any a differential field A extension of and any, the following, any of the following equivalent condition hold. So the first one is to say exactly what you think we are going, is we can't find any DS invariant curve over K, right? So right? So, and the second condition, which is not too hard to see that they are equivalent, but there's still some little things to do, is that for any solution xy in curly S, the transcendence degree over K of K xy is only 0 or 2, all right? So you never get 1. So it's not hard to see that if the transcendence degree is 1, means that there's a polynomial that vanished between x and y. Now it's not hard to check that this polynomial will be DS invariant. Okay, and I would say that here for any differential field extension, I didn't write the K. And usually one assumes that this field K is again a finite extension of C that's sitting in U. Okay. And let me make some remarks. First remark is that the condition 1 was also studied and introduced by Umemura in his study of the Penlove equations. And the idea here is that there's a strong way in which you can connect existence of the invariant curve or non-existence of the invariant curves and strong minimality to the system having so-called classical solutions. So solutions that can be obtained using some classical functions. So I won't say too much about that. But this also is a notion independent of model theory, which with the work with Anand, we discovered that, of course, is now we know is related quite well with strong minimality. All right? And so somehow this seemingly very easy to define notion comes up if you're able to show that your system is strongly minimal, you end up getting a lot of structures theory, so-called trichotomy theorem that you can use then to prove the kind of result you're after. So let me try to expand on that now. But maybe let me make few more comments, so I'll write them down. So first, okay, so the first one I won't write down, I'll just say, I will sometimes, instead of saying that the set of solution is strongly minimal, I will say that the equation itself is strongly minimal. Here, there's no trouble here for Malthus. And then, yeah, go ahead. No? Yeah.
But in your example, so the x equals 0 and the y equals 0,
right.
Aren't those invariant curves? So you're saying that this example is not strongly minimal?
Yes, it's not strongly minimal for this set. But now that's my next note is to precisely say that. Thank you. Beautiful. So this is given a planar system S. Suppose so you already have finitely many invariant, say, polynomial law curve. Let's say over where the system is defined, then you might want to ask instead, are these the only invariant polynomial, right? So you could ask, right? And that's what we will do. So we will say, okay, we already know we have xy, that's an invariant polynomial. Can we show that this is the only one? And what this amounts, it amounts to equivalent to showing that the system together with the condition f1 not 0, fn not 0 is strongly minimal. All right. So indeed, most of the time, certainly from a model theoretic perspective, if you already have, if you know you have finitely many subvarieties like the invariant curve, you can just simply look at the system. So basically, the way I'll state the theorem will then be, I'll add, I want to say, either I can say xy not 0, and now what I'm going to obtain strongly mighty for this system with that condition. That clarifies a little bit. Thank you. All right, so that's exactly what we'll do. Now one might want to ask, what's the advantage of, we want to understand algebraic dependencies among solutions, and what's the use of strong liminality? Well, it turns out that, especially in the case of planar system, autonomous planar system, if you're able to show that the system is strongly minimal, what you obtain is that the structure of algebraic relation is very much constricted. So somehow you can only have binary structures, meaning the only possible algebraic relations will come from pair of solutions. So let me make that precise and then state theorem we use. So definition. So let's say S be strongly minimal. Set planar. Solution set of a planar system, but as I said, I'm gonna make that So we say S is geometrically trivial if for any field, differential field extension K of C and distinct solutions, let's say x1, y1, xn, yn in, let's say, S, and say we don't want to consider algebraic points. So if the transcendence degree of the field generated over K by, let's say, x1 to yn is less than 2n, all right? So it's saying if you are able to see a dependency between the solutions, right, of the system, then there must be a pair of them that you've seen that dependency. Then there is I less than j such that the transcendence degree over k of k with xi, yi, xj, yj is less than okay. So so as you can see, if your goal is to sort of try to prove that n distinct solutions are independent, if you can show that your set is geometrically trivial, what that will reduce is your problem to pairs of solutions. All right, and this has been the strategy in most of the work that I pointed to before, is to first prove that your equation is strongly minimal, then prove that your equation is geometrically trivial, and then finally you're left with dealing with pairs. Now that would be great, but this seems difficult, right? To show that if you have n solution, then you can already reduce to pair. But of course, what I'm hiding here is, as I said already, we have the trichotomy theorem in differentially closed fields, which is a very strong classification. And for autonomous differential equations that are strongly minimal, triviality is automatic. So let me write this down. Oh, and let me just make a comment before that. So see how the conclusion here of the triviality means that if you have a dependency between n solution over k, then you have dependency between pairs over k. You can further reduce it down to C, all right? So if you have dependency over k, triviality is so strong that it says you're going to find this dependency over the field C, all right? I know these are some of the more theoretical magic that unfortunately I cannot say a few words about, but these are the strong tools that has allowed us to make, to prove some of those theorems. So here's the fact. So, all right, so this should be attributed to Reshevsky-Sokolovich, although I think Remy and Martin Hills were sort of reminded us of this result, and one can find a proof of this in the work that I mentioned with Guy Kessar, James Freitag, and myself. But this is really due to Reshevsky-Sokolovich in the trichotomy theorem, and it says, suppose again, this is much more general than that. So it says if you have, so there's a more general definition of strong liminality. So if you have differential equations over the constants, so autonomous, that are strongly minimal, then they will be automatically geometrically trivial. So I'm going to state it only for the case of these planar systems, okay? But it's more general than that. So suppose S is strongly minimal. Planar system over C. Assume, all right, so it's a planar system. So then automatically S is geometrically trivial. And so if it wasn't clear before, why would one want to insist proving strong minimality for these kinds of problem? I hope now it's clear, at least for autonomous planar system. So if you were to have a non-autonomous planar system, say you still have a planar system, but maybe it's defined over a non-constant field, then you don't have such a direct way to get triviality. Then one has to look at the so-called trichotomy, more general trichotomy theorem, and there's one possible case that one has to get rid of, which is the case of what's called Manning kernels, meaning differential equations that live on abelian varieties. But since we are in the autonomous case, we don't have this problem. And so, as you can imagine, my strategy with Newton was to prove this theorem first. Let's prove that it's strongly minimal, and then we get triviality, and then see whether we can handle pairs of solutions, okay? One problem, and I think it's the problem with this entire enterprise of trying to use this small theoretic strategy to prove transcendence result, is that it's very, very difficult to prove that a given differential equation is strongly minimal. So so let me give an example as to why that, and let's stay with the Lotka-Volterra system. All right, so consider, I'm going to take, just for simplicity, LV 1B. Okay, so yeah, so B 1B. All right, so A and C are not present, or 1 here, and B equals D. So what we have is that so this system is not strongly minimal. And it's not strongly minimal even in this more general setting I said. So let's get rid of the x y, the polynomial x times y, and maybe that should work, but it's not. In this case, what you have is, let me quickly write down, it's not hard to see that in this case that if you let x, y be a solution, then check that if you define z to be x minus y, then z prime is b times z. You can check that in 2 seconds. And so in a way, the difference between the coordinate of the solution is an exponential function. All right? And now, so you can consider the field K to be the field Q with the parameter B, and then I joint that Z to it. So that's a differential field. And I claim that over this field, you have infinitely many invariant polynomials. So one can check that for each C in Q adjoint B, so that's my C. So you have that PC, which is the polynomial x minus y minus CZ, is an invariant polynomial. Oh, so I don't know if you, maybe I should put that down. Right. And so why is this, why does this show the difficulty in proving strong minimality? Well, you see, we've added to our field the exponential function, an exponential function, quote unquote. And after adding that exponential function, that's when we found the invariant polynomial. So the definition of strong minimality tells you to look for any differential field extension. So you may add all types of function as your base field, and then try to see whether you have an invariant polynomial. And in this case, if you add that exponential function, you get an invariant polynomial. All right. And so this is a difficulty. The difficulty is you have no control on the field in advance a priori where this will be defined, right? But it turns out this is sort of very recent result of James Freitag, Remy Jawi, and Rahim Musa, that things can be a little bit better. And we use that heavily in our theorem to prove our theorem. So here's what's shown. So yeah, so this is a theorem, as I say, of Freitag, Jawi, and Musa. And again, in a much more general setting, so I'm going to simply state the case of planar system. So suppose S is a planar system or solution of a planar system over C that is not strongly minimal. Then there exists a DS invariant curve over let's say C X Y, where XY is a C generic solution of the system you start with. All right, so what this is saying is that a priori to find DS invariant polynomials, you got to look at any differential field extension. But the result says that it is enough, because you're over the constant here, to try and show that there are no DS invariant curve over the field generated by one solution of a system. So it's a sort of a reflection idea here. All right. And so somehow these are all the model theoretic tools that we've developed over time, which has allowed us to sort of prove the theorem. And so let me end by writing down our theorem for strong minimality, and then say a few words briefly about how the proof goes. Yeah, of course.
So your definition of strong minimality had two conditions.
Right.
One was about the invariant curve,
Right.
and the other was something about the transcendent.
No, so it's equivalent. So one of the two.
Oh.
Yeah, one of the two. Yeah,
Oh,
one
so
of the
you
two.
guys automatically
Yeah.
get lots of the
Right.
curves from that.
So yeah, so somehow, yeah, so finding one usually invariant curve is not problematic in the sense I mentioned before. Yeah, you can cut it through. So the issue is if you have infinitely many invariant curves, then you can't do that anymore. So indeed, there's a notion of dimensional rank. You sort of push the rank up if you have infinitely many such invariants of variety. So and there's a way to say that strongly minimality is equivalent to having rank 1. So if you have infinitely many of these, you push the rank up, so it's going to give you a rank 2. So there's a way in which you make that also. And so anyway, so running out of time, so I write down. Anyway, so the theorem again. So still with Newton self is that so the so assume B and D are linearly independent. Over Q, then so LV A, B, C, D is strongly minimal, and hence geometrically trivial. Oh yes, so thank you. So yes, so I've updated I've updated my LV system by adding the condition that xy not 0. Yeah. Right. Yes. Yes. Yeah, and I did a remark on that. I had a remark that said, when I already have finitely many, I'm going to say that the system, together with a condition of non-vanishing of those. Exactly, no other. Yeah. Yeah, yeah, absolutely. Yeah, thank you. All right. And as I said, so, right, so let me sort of talk a little bit about the proof of the theorem. So, well, what if you are not strongly minimal, right? So it's a proof by contradiction. So if you're not strongly minimal, well, if you look at the second condition that we had in the definition of strong minimality, we had one, there are no DS invariant curve. The other was in terms of transcendence degree. So it tells you that there is K extending C, and let's say UV solution, so that the transcendence degree of over K of UV is 1, all right? And furthermore, we may assume that K is generated by another solution of a system. All right. So what we do then is, and this came from the work joint with Remy Jaoui and James Freitag and Dave Marker, is that somehow that this tells you, in particular, is say that U is in the K. So let's say V algebraic closure. All right, and there's a method. The method we developed there is of a Puiseux series. So you can pass on to Puiseux series. So let me take, just for argument here, to have that U is in the field of Puiseux series in V. And then we can write down the series and differentiate that series. And that will tell you is basically by comparing coefficient is that there is a solution of the exponential, so maybe not y prime. Let's use z prime equals, let's say, mz for some m not 0. And let's say z itself not 0 in K, which you remember was the field CXY. So what I'm saying here is that, and I'll end quickly, is if you start with assuming that you have non-strong normality, and use a Puiseux series argument and look at the conditions of coefficients, what you end up having is showing that that would imply that there must be a solution of the exponential equation in the field generated by one solution. But now you can exploit the fact that this was a solution to the LV system and show that such exponential equation could not exist. All right, so I've run out of time, so this was probably not very satisfactory. But the idea here is, what I wanted to emphasize is, and the work on the Leonard equation, this alone was enough to conclude strong limit normality using the Puiseux series. In this case, we have to somehow do some further analysis about existence of exponential equations, solutions to exponential equations in the field generated by a solution. And you can sort of work with the fact that you have explicit equation to rule out this possibility. And I've run out of time.